Greetings and welcome. Today we will see Unit First of Engineering Mathematics 3, which is linear differential equation with constant coefficient and its applications. We see the basics or the introduction part of the linear differential equation. Here first we see ordinary differential equation and the partial differential equation. Ordinary differential equation is the equation involving ordinary derivative. What is the ordinary derivative? Ordinary derivative is the derivative obtained by differentiating with respect to only one independent variable. That is, the ordinary differential equation involving only one independent variable. Partial differential equation is the equation involving two or more independent variables. Now, first we see linear differential equation. Linear differential equation is the differential equation in which the degree of differential coefficient in each term equal to 1. That is, the linear differential equation having degree 1 or each term having the degree 1. We see the general form of linear differential equation with constant coefficient. Here a naught d raised to ny upon dx raised to n. Here a naught denotes the constant coefficient of the differential coefficient and d raised to ny upon dx raised to n is the differential coefficient or the derivative of order n. Here if we see the equation in which the degree of each term of the differential coefficient is 1. In first, degree is 1, order is n. Here in second, degree 1, order n minus 1. In third term, degree is degree is 1 and order is n minus 2. In this way, we write term up to the an into y is equal to f of x. This type of equation is called the linear differential equation with constant coefficient, because here a naught, a1, a2 up to an all are the constants, and here f of x is a function of x or constant. Now we solve this equation, find the solution of this type of equation. We see this in this unit. For simplification of this, we replace this d upon dx by capital D. Here capital D is the differential operator. If we put d upon dx is equal to d, then here we got dy by dx is equal to dy. Then also we got the value of d square y upon dx square is d square y. D cube y upon dx cube is capital D cube y. Therefore, we substitute all these values in the equation number 1. Then this equation reduce in the form a naught d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 up to a n minus 1 into d plus an. Out of the bracket we take y common is equal to f of x. If we consider this bracket term is the function phi of d, then we got the short form of the linear differential equation is phi of d into y is equal to f of x. Now for finding the solution of this, first we see what is the auxiliary equation. Here if we consider the coefficient of y is phi of d, we equate this phi of d equal to 0. This phi of d equal to 0, this type of equation is called the auxiliary equation. Now we see how to find the general solution of this equation phi of d into y is equal to f of x. The general solution of linear differential equation is y is equal to yc plus yp. That is, for finding the general solution of equation, we find yc and yp. Here yc denotes the complementary function and yp denotes the particular integral. Now first we see how to find the complementary function yc. Now for finding this, we consider the equation, or we consider the linear differential equation phi of d into y is equal to f of x. From this equation we consider only the equation phi of d into y is equal to 0. This equation or the solution of this equation gives the complementary function. For finding the complementary function, To find complementary function, we have to write the auxiliary equation. We know the auxiliary equation is phi of d equal to 0. Solving this auxiliary equation, we got the values of d. That is, the roots of this equation phi of d equal to 0 gives the values of d. Now, from these values of d or root of this equation gives the solution for the equation phi of d into y is equal to 0. Now, we see how to write the solution. If we find the roots of the equation, if we got roots of equation are real and when the roots of equation are real and distinct. If we consider m1, m2 up to mn are roots of phi of d equal to 0, then complementary function is yc is equal to c1 e raised to m1x, that is c1 e raised to first root into x plus c2 e raised to m2 into x, that is c2 e raised to second root into x up to the mth root cm e raised to mn x. This is the solution if we got the roots of the auxiliary equations are all real and distinct. Remember the solution? Now second case is roots of auxiliary equation are real and repeated. If m1 is equal to m2, these are the two roots which are repeated and other all the roots are the distinct. Then we write complementary solution yc is equal to c1 plus c2x. Here two roots are repeated, m1 is equal to m2. Therefore, we take the coefficient of e raised to m1x is c1 plus c2x. If two roots are repeated, then we write c1 plus c2x. If three roots are repeated, then we write c1 plus c2x plus c3x square. And all other terms are the same. Here non-repeated roots are m3, m4, m up to mn. Therefore, we write this solution y is equal to c1 plus c2x e raised to m1x plus c3 e raised to m3x. Here m3 is distinct. Therefore, we write c3 e raised to m3x plus c4 e raised to m4x plus up to the cm e raised to mnx. If three roots repeated, then we write this term in the form of c1 plus c2x plus c3x square into e raised to repeated root into x. This is the second case if roots are real and repeated. Next is case 3. Roots of auxiliary equations are reimaginary. If we consider d equal to alpha plus I beta, here alpha plus I beta and alpha minus I beta are the two roots which are the imaginary. Then we write the yc is e raised to alpha x in bracket c1 cos beta x plus c2 sin beta x. Remember this e raised to alpha x, here alpha is the real part of imaginary root and here beta is the imaginary part of the root, that is e raised to alpha x in bracket c1 cos beta x plus c2 sin beta x. Next is roots of auxiliary equations are imaginary and repeated. Here if we consider d equal to alpha plus I beta are the two imaginary roots, but these two roots are repeated twice, that is we got the four roots alpha plus I beta, alpha plus I beta and alpha minus I beta, alpha minus I beta, that is these two roots are repeated twice. Then the solution is y is equal to e raised to alpha x c1 plus c2 x into cos beta x plus c3 plus c4 x into sin beta x. Here two imaginary roots are repeated. Therefore, we take the coefficient of cos beta x is c1 plus c2x and coefficient of sin beta x is c3 plus c4x. Instead of these two repeated, if two roots are repeated three times, then we consider here c1 plus c2x plus c3x square plus c4 plus c5x plus c6x square. In this way, we write the solution. These are the four cases to find the complementary solution. Here four cases are: first is the roots are real and distinct, second is roots are real and repeated, third is roots are imaginary and distinct, and fourth is roots are imaginary and repeated. Now we see the next method to find the particular integral. Method to find particular integral, that is YP. There are three methods to find the particular integral. First is shortcut methods, second is method of variation of parameters, and the third is general method. We see first shortcut methods. By using shortcut method we find the particular integral. If we got the particular integral, then easily we can write the general solution is yc plus yp. Now we see first shortcut method to find particular integral. Here we use shortcut methods for the functions, special type of functions like e raised to x, sin x plus b, cos x plus b, x raised to m, e raised to x into v or e raised to x into f of x, sin hyperbolic x plus b, cos hyperbolic x plus b, x into v, where v is a function of x. Now we see one by one. First case, if f of x is equal to e raised to x, a is any constant. Now we find the particular integral. Always remember, we write the particular integral in this form: yp is equal to 1 upon phi of d e raised to x. Always remember, always we find the particular integral, we write the particular integral is equal to 1 upon phi of d into e raised to x or function f of x. Now if here e raised to x is the function, then we replace d by a. If we replace d by a, then we got 1 upon phi of a into e raised to x. This is the particular integral if here phi of a is not equal to 0, and we got the particular solution. But if here we got phi of a equal to 0, then we got the case of failure. And if case of failure, then we write the particular solution is yp is equal to x upon derivative of phi of d into e raised to x, and again replace d by a. That is, we got the solution yp equal to x upon phi dash of a into e raised to x. This is the first case. If the function in the form e raised to x, replace d by a. Second, when f of x is equal to sin x plus b or cos x plus b, then yp is equal to, always we write yp is equal to 1 upon phi of d into the function f of x. Now substitute the value. Always if function is either sine or cos or sine hyperbolic or cos hyperbolic, always we write this function in the form of 1 upon phi of d square. That is, try to write the function in the form of d square term, because here our replacement is for d square. Here 1 upon phi of d square into sin x plus b, then replace d square by minus a square. If we replace d square by minus a square, then we got 1 upon phi of minus a square into sin x plus b, provided phi of minus a square is not equal to 0. Here if we got equal to 0, then here we got case of failure. And if case of failure, then always remember we take multiplying by x upon the derivative of phi of d, and again replacement for d square, replace d square by minus a square. Therefore we got yp is equal to x upon phi dash of minus a square sin x plus b, provided phi dash of minus a square is not equal to 0. If we got this phi dash of minus a square equal to 0, then again we got case of failure. If we got case of failure, then we write x square upon phi double dash of minus a square. And we use the same rule for cos function. Now we see the case 3. If f of x is sine hyperbolic or cos hyperbolic. Remember here, in trigonometric function, we replace t square by minus a square, and in hyperbolic function, replace t square by plus a square. This is the difference between trigonometric and hyperbolic function. Now, use the same procedure to find the solution. Procedure is, first we write the function in the form of 1 upon phi of d square into sine hyperbolic x plus b. Here, replace d square by a square. If we got phi of a square is not equal to 0, then this is the solution. But if we got equal to 0, then case of failure, then here we multiplying by pi x. We write the derivative of denominator, that is we write derivative of phi of d square with respect to d, and in last replace d square by a square. Next case, case 4. When f of x is equal to x raised to m, where m is positive integer, then we find the particular integral. Always we write particular integral is 1 upon phi of d into x raised to m. Remember this, 1 upon phi of d into x raised to m. If your function is x raised to m, always we write this phi of d in the form of 1 plus function of d or 1 minus function of d. We write this in the ascending increasing powers of d. For this we use the standard expansion 1 upon 1 minus x or 1 upon 1 plus x. We use this expansion. For this always we write this 1 upon phi of d in the form of, or we write denominator in the form of 1 plus function of d. For this, if in phi of d, if constant term is there, we take the constant term outside and we write the function in the form of 1 minus x or 1 plus x. But in the denominator, there is no constant term, then here we take the lowest degree term of d outside. If we take the lowest degree term outside, then we got the function in the form of 1 minus x or 1 plus x, or 1 minus function of d or 1 plus function of d. And we use the expansion. First is 1 upon 1 minus x. Here expansion is 1 plus x square plus x cube up to the next. And we use 1 upon 1 plus x. Here value is 1 minus x plus x square minus x cube plus up to next. We use expansion and we operate this on the function x raised to m. Here, if we operate, then we got the solution of the given equation. Next case is case 5, when function f of x is equal to e raised to x into v, where v is a function of x. Here we find the particular integral. Always we write 1 upon phi of d into e raised to x into v, that is 1 upon phi of d into f of x. Here f of x is e raised to x into v. If the function is in the form e raised to x into v, always we take e raised to x outside and replace g by d plus a. That is, we write this is in the form of, this is equal to e raised to x in bracket 1 upon phi of d plus a into v. Replace d by d plus a, and we solve the bracket term by using 1 to 4 cases which is applicable. And the last case, when function f of x is equal to x into v, where v is any function of x, then we write yp is 1 upon phi of d into f of x, where f of x is x into v. Then for simplification we use the formula x minus phi dash of d upon phi of d, and the out of bracket we write 1 upon phi of d into v. By using this formula we find the particular integral, where this 1 upon phi of d into v is not case of failure. These are the shortcut methods. Here we see how to find the complementary function and how to find the particular integral by using the shortcut method. We see the next method of variation of parameter and the general method in the next lecture or next video. Thank you.